Good morning out there. We're talking here today about Math 111. And today we're going to talk about section 7.5, not 7.4. We're going to skip 7.4 and talk about 7.5, solving radical equations. Alright, for the test, let's take a look back at what we covered in Chapter 7. Chapter 7, we talked about 7.1. We skipped 7.2. Oh, no, we did not skip 7.2, excuse me. 7.2, 7.3. Let me put some titles on here. Here, 7.1, we talked about radical expressions. 7.2, we talked about rational exponents. In 7.3, we talked about simplifying radicals. And 7.4 we're going to skip. Not that it's not important, but I really want to get to 7.5 and spend quality time on this solving radical equations. In algebra, in mathematics, solving equations is really what it's all about. That's the goal behind all these algebraic manipulations. Alright, solving radical equations is something I bet we've done before. For example, let's jump right in. Solve the square root of x plus 3 equals 4. Well, I think you can agree with me. I can square both sides of this equation. I know that if I take the square root of anything, let's say the square root of a, and I square it, I'm really just reversing the root operation. Basically, the squaring operation undoes the square root operation, and I get a back. Well, of course, that's if a is positive, right? We cannot have roots of negative values. All right, so loosely speaking, I'll say the square root of a, the square of the square root of a is a. So I can square both sides here. And if I square the square root of x plus 3, I just end up with x plus 3 on the left-hand side equals 16 on the right-hand side. So if x plus 3 equals 16, x then equals 13. Now I call this a candidate for a solution, not a solution until we check it. In all these radical equations, you must check your answers. Right, the idea here is when I square both sides of an equation, I may be introducing extraneous, or what they sometimes call false roots, into the equation, as we'll see. Alright, so you must sub your answer back into check. So if I take the square root of 13 plus 3 and plugging in 13 for x and ask, is that a true statement? Of course, 13 plus 3 is 16, and the square root of 16 is indeed 4, so x equals 13 is indeed the answer to this equation. Alright, so in primary strokes, that's how it goes, and let's build up some sophistication here and do something a little more difficult. How about if I ask you to solve the square root of 3x plus 1 equals x? Well, I suppose in any of these radical type equations, the first thing you want to do is isolate the root sign, isolate the radical first. Right, so then we can raise both sides to whatever power we need to get rid of the root sign. So here I'm just going to subtract 1 from both sides, and you'll see then I've got a root expression on the left-hand side all by itself. We will then square both sides. Now you got to be careful here because, of course, on the right-hand side we now have a variable expression. On the left-hand side, the square root of 3x plus 1 squared yields me a 3x plus 1, right? The second power function and the square root function are inverse functions, so they undo each other. On the right hand side, be careful. If I square a binomial, you've got an inner and outer product to deal with. So if I square x minus 1, I get x squared minus 2x plus 1. Alright, clearly I've got a degree 2 equation brewing here. Let me get it in standard form. In other words, I'll get everything over on the left hand side. I'll subtract 3x and subtract 1 from both sides. I'll get a 0 on the left equals x squared minus 5x on the right. Alright, we still need to solve. We still need solutions for x. This gives me a degree 2 equation, which I can solve by factoring, right? We did this before in chapter 5, which of course will be included in the next test. I'll factor the right hand side. Alright, so just a GCF factoring, that's all there is to it on the right hand side. So x times x minus 5 equals 0. So I've got two solutions, x equals 0 or x equals positive 5. Now remember, these are candidates for a solution. You must check to make sure they work by subbing them in to your original equation. Right? Root 3x plus 1 equals x. Let's try it. Square root 3x plus 1 equals x. So I'll plug in x equals 0 and see if it works. 3 times 0 plus 1, does that equal 0? Everywhere I see an x, I plug in a 0 and see if I have a legitimate statement here. Well, 3 times 0 is 0, and 0 plus 1 is 1, so you have the square root of 1 plus 1. Is that equal to 0? Of course it's not. Alright, so this solution, this candidate for solution x equals 0, I have to strike it. It did not check. It is a false or extraneous solution. So let me write that down. X equals 0 is a false solution. Alright, so I have to strike it. How about x equals 5? Well, we'll have to check it out. The square root of 3 times 5 plus 1 equals 5. Let's see if that works. 3 times 5 is 15. 15 plus 1 is 16. So I have the square root of 16 plus 1. And is that equal to 5? Of course it is. The square root of 16 is 4. And 4 plus 1 equals 5. So indeed, that does check. So x equals 5 is my only solution for this problem. So my solution is x equals 5. X equals 0 is stricken. Okay? Alright. Let's try another one here. Let's see if I can fit one in this screen here. How about, now I'm going to need a new screen. Hang on. There we go. How about equations with two radical symbols in them? Something a little even harder. Equations with two radicals. How are we going to handle this? Alright, now I notice on the right hand side there's an implied product there. So what I'm going to do is square both sides. To get rid of those root signs, get rid of those square root signs. I got to be a little bit careful on the right hand side. Let me take care of the left hand side. I know the square root of something squared is just that radicand back. Basically the root operation and the power operation undo each other. Now you got to remember, on the right hand side you've got two factors being raised to the second power, so you've got to square both independently. So 2 squared is 4, and the square root of 3x plus 4 squared is just 3x plus 4. Okay? Alright, so applying my distributive law and working things out a little carefully, I can now turn this into really a chapter 2 type equation. 4 times 3x is 12x, and 4 times 4 is 16 on the right hand side. If I then, well, I suppose I would subtract 5x from both sides, and then let's see, subtract 16 from both sides. I'll have my x term remaining on the right hand side. Then I'll get 7x on the right equals 9 minus 16 is minus 7, and I get a candidate for solution of x equals minus 1. Now remember, because of that squaring process, you may be introducing false solutions, but you're not sure until you check. So you must check your answers in these root equation type problems. Well, I'll go back to my original equation, and I plug in the candidate. Well, I've only got one candidate here in this one. X equals minus 1. Alright, so everywhere I see an x in my original equation, I plug in a minus 1. And let's see if I can reduce this to an equivalent statement. Well, 5 times minus 1 is minus 5, plus 9 is 4, so I end up with the square root of 4, or 2, on the left-hand side. How about on the right-hand side? 3 times minus 1 is minus 3, minus 3 plus 4 is 1, and 2 times the square root of 1 is, of course, 2. So both on the left and right-hand side, I get confirmation. So my solution for this equation is x equals minus 1. Okay. Alright, things get nastier. Let's take a look what I'm talking about. I believe this one's out of your homework list, number 19. The square root of 1/3 x minus 2 equals 8. Let's see, I want to solve for x. Well, I'm going to square both sides here. Yes, it does involve fractional arithmetic, but don't panic. If I square both sides, I can essentially get rid of that root sign on the left. And of course, 8 squared is 64 on the right. Alright, now it looks like a chapter 2 equation. How do we solve something like this in chapter 2? Basically multiply both sides by the LCM of all the coefficients. Well, of course, that's 3. So I've got to apply my distributive law on the left. 3 times 1/3 x is just x, minus 3 times 2 is 6, equals, and 3 times 64, let's see, 204, I believe it is, right? 3 times 4 is, hang on a minute. 3 times 64 is 192. Is it not? 3 times 4 is 12. Carry the 1. 3 times 6 is 18. 192. Looks good. So now I can easily solve for x. X is 198. Now remember, this is a candidate for solution. We must check our answer. So let me go back to my original equation. Square root of 1/3 times x minus 2 equals 8, and I have to ask myself, is that a true statement? So 1/3 times 198, well, 3 goes into 198 66 times, minus 2 equals 8. Is that a true statement? I think we can see that it is. 62 minus 6 is 64, and the square root of 64 is 8. So my candidate checks out. So my answer here is going to be 198. Solution, x equals 198. Okay? Alright, let's do a couple more of these root type equations. I believe this is number 33 from your homework list. Now, again, square roots are not the only roots in the woods. We also have the possibility of order 3 or index 3 roots, or even higher index roots in these root equations. Alright, so we got the cube root of n minus 1 equals 3. Alright, well here, to get rid of this cube root sign, I'm going to raise both sides to the third power. Hopefully everybody believes that without too much convincing. If I take the cube root of something and then raise it to the third power, the third root and the third power are inverse functions, and you get back with what you started, namely here a, for this side example here. Alright, so I can apply this over here and say the cube root of 7 minus 1, 7n minus 1 to the third power is just 7n minus 1, and on the right 3 cubed is of course 27. Alright, so not too bad. So I'll add 1 to both sides. So 7n equals 28, and n then equals 28 over 7, which equals 4. Now I circled it, and that's maybe a bad habit to get into here because it's a candidate. We're not sure yet if it's going to work. Alright, so we've got to check. The cube root of 7 times n, well, we're going to throw in n equals 4, minus 1, is that indeed equal to 3? Well, 7 times 4 is 28, and 28 minus 1 is 27. So on the left-hand side, I see the cube root of 27, and that should be equal to 3. Yes, it is. So my solution checks, my candidate for solution checks, so I've got a final solution of n equals 4. Alright, let me get a fresh screen here. Alright, how about, this is number 43 on your homework list. They give us a radical expression in function form. Okay, so f of x equals square root of 2x squared minus 7x. And they ask us this question: for what values of x is f of x equal to 2? Well, I suppose you could talk a lot about this problem, but the long and short of it is, well, if you want your function to be equal to 2, I'll just set my expression equal to 2 and solve for x. So set equal to 2 and solve for x. Okay? Alright, so I've got a root expression. Doesn't look too bad. I'm going to, let me rewrite this. I'll start out with 2x, the square root of 2x squared minus 7x equals 2. Clearly I'm going to want to get rid of this root sign on the left, so I'll square both sides. I know the square root of something squared is something. So I can simplify that left-hand side, then is 2x squared minus 7x, and on the right, 2 squared equals 4. Alright, so clearly we're going to get a degree 2 equation out of this once I square both sides. So I'll put it in standard form. Solve degree 2 equation now. And we've really only got one way to solve a degree 2 equation, and that's by factoring. And I think I can break down this trinomial into a product of two binomials. So I'll say 2x plus 1 times x minus 4 equals 0. Let me check it. The first product is 2x squared. The outer product is minus 6x. The inner product is, the outer product is minus 8x. The inner product is 1x. And the last product is minus 4. So indeed it does check out. Let me rewrite it. Alright, so once I've factored it properly, I can set each factor equal to 0 and then solve. So I get x equals minus 1/2 on the left, or x equals 4 on the right. Now remember, these are candidates. We must check them both. Alright, so let me go back to my original equation. Let me check minus 1/2 first. Alright, so if I got the square root then of 2 times minus 1/2 squared minus 7 times minus 1/2, does that equal 2? Let's try it. Minus 1/2 squared is 1/4, and 2 times 1/4 is 1/2. Minus 7 times minus 1/2 is plus 7/2. Again, on the left, 1/2 plus 7/2 is 8/2 under the root sign. 8/2 under the root sign is 4, and the square root of 4 is, of course, 2. And 2 does equal 2, the original right-hand side. So I claim that checks. Let me go back up screen here. So x equals minus 1/2 indeed is a checked solution. Okay? Let me try it with x equals 4 now. Does x equals 4 check in my original equation? Let me rewrite, put it in a different color so we can see it a little more clearly. I'll start out with my original equation, and I'm going to plug in x equals 4 everywhere I see a x. So 2 times 4 squared minus 7 times 4, the square root of that equals 2, and I ask myself, is that a true statement? Well, 4 squared is 16, 2 times 16 is 32, and 7 times 4 is 28. So I want the square root of 32 minus 28. Well, of course, 32 minus 28 is 4. So under the root sign, I've got a 4, and the square root of 4 is indeed 2. So this solution, x equals 4, also checks out. So let me write down, we'll go to the bottom, my final solutions. Both of them work, both of them check. X equals minus 1/2 or x equals 4. Alright, so if you can handle this one, you should be able to handle all of them. So we're hitting the 25-minute point. I'm going to call it a day. So this concludes section 7.5, Solving Radical Equations.